Hello YouTube, welcome to my workbench. I've been watching the ExplainingComputers.com YouTube channel test several different cooling solutions for the Raspberry Pi 4. Unlike previous Raspberry Pis, this one does get relatively hot. Most of those cooling solutions only address the system on a chip here. However, a few of them would also address the USB and the Ethernet chips as well, and some even would have a heatsink on the RAM. However, none of those solutions addressed some other components that also get very hot, although not as hot as the system on a chip. And that is these voltage regulation components over here by the USB-C connector. Now, of course, these all look to me to be far too small to put heatsink on, so not much you can do about that, I suppose. Which is why today I'm going to try a cooling solution that does not rely on any heat sinks at all. So this will be our test unit, and this is a Raspberry Pi 4 with 8 gig of RAM. We have a small TFT LCD display. I don't think we'll be able to see that in the video because of the brightness and the size of it. But we have it mounted to a right angle header here, so it doesn't block any airflow going to the surface of the Pi, especially going to the processor here. And we also have this temperature and humidity sensor, so we'll be able to monitor the ambient temperature. So I'll be running a similar script to that used by the Explaining Computers channel, with a few minor changes. I print out the date and time at the beginning and end. This should take about 11 minutes. In the tests that channel ran, the best cooling solution gave a temperature rise of 12 degrees over ambient. So that's the number we're going to try and beat today. So to that end, I have created the Raspberry Pi Blast Cooler. It has a 120 millimeter fan, a duct, and 4 standoffs to mount the Raspberry Pi to. This fan is a 48 watt fan. It spins at about 6,000 RPM. And so I think this should do the job. It is a little bit louder by a few dB than the fans you normally find on a Raspberry Pi. That's if you consider 30 to 40 a few dB. So let's mount the Raspberry Pi to this and start the testing, see what happens. Ignoring the first data point, before the system on a chip temperature stabilized, the temperature difference varied from 13.2 to 15.4 degrees, with an average of 14.2 degrees. That's disappointing. I was hoping to do better than 12 degrees. Even so, the temperature of the system on a chip was kept well below the throttling threshold of 80 degrees. There are other, even crazier fans out there I could try, but I may need to add a small heatsink to be able to get to that 12 degrees. When a cooling solution requires more power than the device you are cooling, it's clear it's not the best design. Of course, this isn't a practical cooling solution, but it was fun to try. It would be interesting to see if this helps the voltage regulator supply more power, since I'm sure this cools that part of the board better than any other solution I've seen. If I get a more powerful fan, or decide to try this with a heatsink, I'll post another video to show the results. I didn't give a very good view of the blast cooler in the video. Here is a screen recording of the 3D model. We have the fan, the duct, the standoffs, and the Raspberry Pi. Taking a look from the fan end, you can see down that way. And then to get a view from the side, you can see it that way. Alright, if I hide the Raspberry Pi, the standoffs, and the fan, you can see the duct better. So looking from this end, we can see a cone in the center, which is designed to help direct the airflow around the fan hub, with curved fins that hold that hub in place. Those curved fins match the same curvature as the fins that hold the hub motor in place. Now looking from the other end, we can see how those fins go from the wall of the duct to the hub in the center and hold that in place. Alright, that's the end of our video. Until next time.